Alright, so in this video I'm gonna be explaining another important article with the title Understanding Virtual Nodes, Oversmoothing, Oversquashing, and Node Heterogeneity. So this important paper in 2024 from Michael Bronstein in Oxford. Message passing neural networks have been shown to have limitations in terms of expressivity and modeling long-range interactions. Augmenting message passing neural networks with a virtual node removes the locality constraint of the layer aggregation and has been found to improve performance on a range of benchmarks. We provide a comprehensive theoretical analysis of the role of virtual nodes and benefits thereof through the lenses of oversmoothing, oversquashing, and sensitivity analysis. First, in contrast to prior belief, find that virtual nodes typically avoid replicating anti-smoothing approaches to maintain expressive power. Second, we characterize precisely how the improvement afforded by virtual nodes on the mixing abilities of the network and hence in mitigating oversquashing depends on the underlying topology. Finally, we highlight that unlike graph transformers, classical instantiations of virtual nodes are often constrained to assign uniform importance to different nodes. Consequently, we propose a variant of virtual node with the same computational complexity, which can have different sensitivity to nodes based on the graph structure. We show that this is an extremely effective and computationally efficient baseline on graph-level tasks. So while graph transformers incur a large memory cost, a significantly more efficient method that incorporates global information in each layer to combat oversquashing is adding a virtual node connected to all nodes in the graph. This is widely used in practice with the empirical successes. However, besides recent work connecting virtual nodes to graph transformers, a few efforts have been made to analyze in what way and to which extent virtual node improves the underlying model. So we find the gap between virtual node and graph transformer. You know that we have aggregation function and update in any graph neural network, which is traditional. But it has this limitation of one hop for each node. So you need k layers to get k hop from one node to another node, which is k distant away. So graph transformer, which is an extension of message passing neural network class, is given by graph transformers where a global attention mechanism connecting all pairs of nodes augments the one-hop aggregation. Graph transformers increase the expressive power of message passing neural networks by heavily relying on structural and positional encoding, and entirely bypass the issue of oversquashing, since the global attention breaks all potential bottleneck arising from the graph topology. This comes at a price, because you know that it has graph transformer have quadratic memory costs, so we cannot use it. So message passing neural network with virtual nodes, an alternative approach to enhancing message passing neural network without leading to significant memory costs of graph transformers, consists in introducing a virtual node connected to all other nodes in the graph. A standard formulation of message passing with virtual nodes, referred to as message passing neural network plus virtual node. So this is the update. So not only you have this traditional approach, but also you have this virtual node update, some additional nodes. We call them virtual nodes. So let's look at the interactions. They depend on themselves. Also, they depend on the aggregation on the virtual nodes. But here J is in vertices of the graph, and J here is in the neighbor of the node I. So we know this, so let's focus on this one, which is about aggregations of virtual nodes. So augmenting message passing neural network virtual node have often been shown to improve performance. Nonetheless, a careful analysis of how and when virtual node helps is still lacking. So pair norm, I think I explained it in previous video. Pair norm. Methods such as pair norm aim at mitigating oversmoothing, which occurs when the node representations converge to the same vector in the limit of many layers, independent of the task. To address the claims in K and compare it with pair norm, we adopt assumptions and other theoretical works on oversmoothing and consider networks whose layers are linear. In particular, to assess advantages of message passing neural networks and virtual nodes over pair norm, we studied their expressivity. Since aggregating M linear layers yields a polynomial filter of this form, and here H are the input node features, we choose as expressivity metric precisely the ability of a model to learn such polynomial filters. In fact, under mild assumptions, polynomial filters are comparable to the 1WL test. Additionally, when the input features are constant, polynomial filters coincide with graph moments, a metric of expressivity studied in this reference. So measuring expressivity with polynomial filters. Since this section we restrict the analysis to models that have linear layers, we introduce simple message passing neural network baseline. So we just choose a sum aggregation and a linear update with a residual connection. With WL is a D by D matrix, and H is a N by D feature matrix at layer L. Similarly, for message passing and virtual nodes, we consider layer update with mean aggregation for virtual nodes. So similarly, up to this point we know that we also add another term, where Q is a weight matrix and the vector of ones. For simplicity, we assume that the output after M layers Y sub M also has dimension D, and choose a mean pooling operation in the final layer, so that given a weight matrix theta, we have this Y sub M, which is theta mean of H, with H computed by either 3 or 4. We can express Y as a graph-level polynomial filter. You know these A to the K's, because A is adjacency, so it looks like a diffusion that I've explained several times. So these polynomial filter diffusion, propagation method, all of them are related to eigenvectors in spectral graph theory All of them are the same thing, really, but their names are a bit different. So there are polynomial filters that can be learned by MPNN. So don't forget that theta here is just the some parameters. And we have m layers. So k, for example, a h theta plus a2 h theta 2 plus a3 h theta 3. But theta, these is going down. The weights should go down in order to, first of all, converge this time series. So the weights of the higher hops, let's say, is going down. It is reducing the global effects as the number of m, as the number of layers is growing. So as I said, we have these additional virtual node updates. We have aggregation, very simple sum aggregation, and then updated. So sigma is a pointwise nonlinear map. A is a potentially normalized adjacency matrix. Omega is a weight matrix. Then we have this psi and psi vn are learnable message functions. N tilde depends on normalization choice. And the key observation is that this equation 6 coincides with message passing neural networks of Giovanni in 15, but operating on multi-relational graph with this adjacency matrix, where edges connecting virtual nodes to nodes in G have different types. Yes, there is another article. They use relation. For example, in their rewiring, they said that, okay, if we rewire, for example, then we put a special label over that so that we distinguish different kinds of edges. So that otherwise you have changed the topology, and that is not good. That is you have changed the intrinsic property of your graph. So to assess if and how virtual nodes help mitigate oversquashing, we need to determine whether the commute time of G is smaller than the commute time. Commute time between two nodes, it goes and come back. So if you H1 and H2, if you add these two times, then you get the commute times. And H1, usually we call it hitting time. Hitting this and then coming back, hitting another, hitting source and target. If you add them, you get the commute time. But whether the commute time is smaller than the commute time of the original graph. Below, we let V be an orthonormal basis of eigenvectors for the Laplacian with associated eigenvalues. So the commute time between nodes after adding a virtual node changes as this. It's very interesting. So after adding a virtual node, the commute time is now different. The distance between their commute times shouldn't be significant, shouldn't be too much. And it's only dependent on these variables, the distance between I and J, also the lambda sub L. In particular, the average change in commute time can be, so if you just add the average, then you get a better measure. So Di Giovanni introduced the notion of mixing to formally assess the amount of interactions between I and J required by the underlying task, and compared it to mixing induced by a message passing neural network prediction after M layers. So, inspired by this 11 that they are homogeneous, the layers are homogeneous, to allow for more heterogeneous sensitivity through the virtual node, we propose this update, a simple variation to message passing and virtual node, with the same computational complexity. So we combine the local and non-local representations. And this Jacobian, we have seen this in several papers about oversquashing and oversmoothing. So it's a very important measure. We see that the sensitivity of node I to feature K is a function of graph topology. The message functions evaluated over neighbors of K. In particular, our proposed variation uses the same message functions to learn a heterogeneous global update. And they have some ablation study to what extent does message passing and virtual node replicate per norm. How does adding a virtual node affect the average commute time on real-world graphs? Which tasks show a gap between message passing neural network and virtual node and graph transformer due to node heterogeneity? So these two data sets are very important in biological data sets. And you see that they compare it with, for example, GCN, gated GCN. I think this is delay message passing of Mike Bronstein, if I'm not wrong. X-former, and their method here has this. Best results are in green. So over 10 runs, so you see some variance, plus minus something. And so you see that PEPT struct is much harder. PEPT function state of the art is 68%.